Here you go. Okay, so the circuits are in parallel. 5 volts, 5 volts, 0 volts here, 0 ohms across the switch, 47 ohms for the first resistor, 100 ohms across the second resistor. And what's the theory again? The theory again is the one that I showed to you before. Here you go. For circuit in parallel, we have a equivalent, oh, not this one here, sorry. For circuits in parallel, we have an equivalent resistance that's given by this value right in here. In PowerPoint format, let's go get it. Here you go. Here you go. That's what we have. 2 resistors in parallel. If I want to make it look like you have in there, I have to rotate this guy. Right? Here you go. Let me copy and paste. Now, oh, what did I do here? What's going on here? Yeah, here you go. Here you go. Circuits in parallel. Choose your circuit. I'm going just to orient this guy in the same way that is oriented there in the simulation. Okay? Here you go. Group. I will rotate that. See that? That's how it is represented there in the simulation. Here is the power supply, and by the way, the power supply there, the positive is on the top and the negative is on the bottom. That, here you go, negative and positive. This one is R1, this one is R2. Okay? That's how in the simulation there. But of course, the same circuit can be illustrated like that. So let's look at the circuit and let's study exactly how it works. Here we have one track of my circuit. Electrons can flow through it. But then we have a second track here, this other one. So electrons, the current is going to flow from the battery, from the positive of the battery, and it's going to reach here, this fork in the road, this node. We call it a node. Okay? And at this point, electrons are going to decide whether they're going to go this way or whether they're going to go this way, just like cars in a fork, approaching a fork in the road, just like cars. That's a very good analogy. And what do you have? We have a current flowing from the battery. Here's the current exiting the positive of the battery and approaching the negative of the battery. Reaching here, right here. Okay? What's next? When you get to the node, or let's say the fork in the road, the current splits. Some of the electrons flow through here, the remaining of the electrons flows through here. Here you go. Keep with the let's use this one. What am I doing? Here you go. And once they reach this point, the current I1 and I2 is going to be combined. Okay? Because the two resistors are connected in parallel with the battery, the potential difference here is going to be the same as the potential difference here and the potential difference here. The voltage in this case is not split. They are the same. But the current is split. Okay? So I'm going to, an important difference between circuits in series and circuits in parallel. Here you go. Circuits in series. The voltage are split between resistors. But the current is the same. Okay? V1 plus V2 is V. I1 is equal to I2 is equal to I. In parallel is all the way around. The voltage is equal and the current combines. That's easy to memorize, right? It's either equal or sum. It's either equal or it's a sum. One is, if one is a sum, the other, which is the current, is going to be equal. If one, the voltage is equal, the other, in the other circuit, is going to be, for the current, is going to be a sum. That's how it works in a circuit in parallel and circuit in series. And you can visualize that very well just by these simple drawings that you see here. Okay, the voltage is the same. V1 is equal to V, V2 is equal to V. Okay, here you go. I'm gonna get this guy. Like that. And don't forget, we can combine those two resistors. I'm going to do the following. Here you go. Picture that here. Combine those two resistors. Here you go. Oh, I'm gonna make it transparent. Color. Let's see. No, the transparent is supposed to be. Here you go. I got the wrong one. This one is supposed to be transparent. Here you go. See, when we combine those two resistors here, we go to the next step, and I'm gonna put dashed, so you know that we are combining them. Here you go, like that. Here you go. Dashed lines. Like that. Here you go. When you combine those two resistors in parallel, what we get next? We have an equivalent resistance. From there, we can use Ohm's law to calculate the current exiting the battery. The simplest of all circuits, equivalent circuit. Okay? And that's what he's gonna ask you next time. Get used to draw those diagrams. They're very simple. Doesn't require any fancy drawings. That's why physicists and engineers invented this type of diagram. So let's see what he wants. Are the resistors in series or parallel? Are these resistors in series or in parallel? Or in parallel? Is the current the same for these two resistors? No, they're not the same. Is the voltage the same across these two resistors? Yes, they are the same. Find the equivalent resistance. Go ahead, now we're going to do resistors in parallel. Here we go. I'm gonna copy and paste that and just change some stuff here. Here you go. Okay, the voltage is the same, resistance is the same. What we end up having is Ohm's law, right? But now the equivalent resistance is going to be different. It's going to be the sum of the inverse, right? Sum of the inverse, like that. Okay, I'm going to need this equation. Let's see here. Let's see what I can do. Maybe we don't need this one. I think it looks like I have to go, from scratch. Let's go from scratch. I'm going to simplify this equation. Here you go. Like that, see? Sum of the inverses. He wants you to calculate the equivalent resistance. I'm going to do step by step here so you can see. I'm going to substitute R1 here, and I'm going to substitute R2 there. So hopefully it's not going to solve for us. Yeah, here you go. That's exactly what I want. Didn't automatically solve for us. See that? That's what we get. I can sum those two, right? But I want to get the equivalent resistance, not the inverse of the equivalent. So we solve for the equivalent resistance. We combine that under the same denominator, invert, and calculate. 31 ohms, 31.9 ohms. That's the equivalent resistance that I'm getting. Find the theoretical value for the source current. Okay, now we can find out the theoretical value for the source current. Current is going to be given by, here you go, V equivalent resistance. So let's go ahead and I'm going to drag here to this spot. V omega is amperes. V over omega is amperes. And that's what I get for the current across, not across, but the current leaving the battery in the circuit with parallel resistors, 0.156. That's 156 milliamps. They start to become a rather large current, but it's still safe. Okay? That's the current of the source. I'm going to put here, I sub S. No, that's okay. No, that's okay. Don't do that. Leave it like I. My I is I sub S. So next, he wants you to calculate I1 and I2. How do I get I1 and I2? We use, Ohm's law, R1 times I1. And we do the same for the second resistor, just like we did before. V2 is R2 times I2. We're gonna go to calculate that. You go, calculate that. V1 equal to V, because the circuit, the resistors are in parallel. Here you go. V1 is equal to V. V2 is equal to V. Like that. V is equal to 5 volts. I'm gonna just copy this one and make it, keep it closer. Right? V2 is equal to V. Let's see here. Okay. Yeah. Okay. V. 5 volts. 5 volts. R1 is 47. R2 is 100. Okay. R2 is 100. Here you go. Let's not forget that V over ohm is amperes. Okay, here you go. I'm going to substitute here. I'm going to substitute here. Calculate. Calculate. Not clarify, but calculate. Here you go. That's what I'm getting for the current. Current through the first resistor, current through the second resistor. The second resistor has a higher resistance, consequently has a lower current. First resistor has a lower resistance, consequently has a higher current. So you can go ahead and put the theoretical values here, and you know, because it's in parallel, V1, delta V1 is equal to V. And delta V2 is also equal to V. Now we're going to perform the simulation to get the experimental values. Okay? Going there. Show the current. Here you go. Here's the current flowing. See? You can see the arrows moving. But check the arrow here. See that? The arrow here is moving slower than this arrow. See that? Because we have a higher resistance. Higher resistance. Charges move slower. So let's get another break. It's 2:48 now. Let me see how you're doing. Any questions, folks? Let's see. Bella, are you there, Bella?
Yes.
Okay, any questions?
No questions.
Okay, do you understand what's going on there, Bella?
Yeah.
Okay, good. Have you ever seen those circuits before? Have you ever seen
No.
anything like that? No? First time you've seen that?
Yeah.
Oh, I see. Annabella, are you there, Annabella?
Yes.
Okay. Yeah, you barely came through. Okay, so.
Yes, I'm here.
Okay, yeah, okay. So a little bit muffled, your voice. Okay, Sarah. Are you there, Sarah?
Yes, I got it.
Okay.
I'm here.
Any questions, Sarah?
No questions.
No? Okay. Carly.
Yeah, I'm here.
Okay. Mahedi.
I'm good.
You're good? Okay. Wesley? Let's see, Wesley. Yeah, okay, good. You're in good shape, Wesley. Any questions? Do you have any questions, Wesley? No? Okay, good. Ada. Are you there, Ada?
Yes.
Oh, okay, good. Yeah, now I hear you. Okay, good. Okay, any questions, Ada?
No.
Okay, thank you. Here you go, Jordan.
Yeah, I'm here.
Okay. So, Donica.
Here.
Okay. Shagar.
I'm here.
Okay. Daniela Rodas.
Here.
Okay. Dior.
No questions.
No question. Thank you. Treya.
No questions.
Oops. Thank you. Peter.
I don't have any questions.
Okay. Ana Ponce. I can't hear you, Anna. Looks like your mic is disconnected. Turned off. Oh, okay. I got it. Thank you. You put chat. Okay. Kaylee.
Here.
Okay. Alisa. No questions. Good. And Jasmine.
No questions.
Okay, good. So let's go ahead and have our break. 2:51 right now. Let's go to 3:06. Break until 3:06. Lab notes. Break till 3:06 p.m. Okay, see you soon. Again, here you go. Here's the circuit together. I put the ammeter in there. Let me see if you missed something. Here you go. Here is the, okay, so far you have already done that, and now we are going to do that. Current coming out from the battery. Let's see if there's anything else that we missed along the way. Yeah, it doesn't look like we missed much, right? Ammeter. Go again to the instructions of the simulation. What am I measuring here? I'm measuring 0.60 amps. Is that what I got for my simulation? Let's see. My simulation is, yeah, it's 0.156, which we round up to 0.16. So go ahead, write that down in your table, and don't forget, use, put the units there. In the table on this line. Oh, nope. Here you go. Put the units between the parentheses. Between the parentheses. Between the parentheses. Between the parentheses. Okay. We have the theoretical values. We are doing this one right now. We're doing the experimental value right now. We're going to do the next one. We're going to know the current flowing through the first resistor, I1. We're gonna split this circuit, this part of the circuit, move the resistor a little bit down, and place my ammeter here. Okay, oh gosh, now I gotta get this thing, fixed. Yep, lined up properly. So it looks nice. It doesn't have to, but yeah. Yeah, that's the best I can do. I'm not gonna do more than that. Otherwise I'm gonna end up struggling here, right? 0.11. Is that what we got for my, yeah? 0.106, which is, we can be rounded up to 0.11. And then we put another one here. Here you go. Let me see if I can fit it. Get the current meter. Okay, here you go. Let's see if I can fit it here. Yeah. Oh, almost. Yeah. Oh gosh, it moves out everywhere when you do that. There you go. Better, huh? 0.05. Is that what you are getting there? Let's see if it's what you are getting there. 0.05. I choose. Yeah, that's what I'm getting. 0.05. Okay. What's next? Oh, delta V1, delta V2. Let's get our multimeter and let's verify that we're getting delta V1 and delta V2. Here you go. That we're getting the same voltage of the battery. Negative. Oh, I want that. I want to put that here. Negative here. Positive here. Positive is facing the battery. 5-volt battery. Let's go to the values. Here you go. Values 5-volt battery. 5 volts drop in the resistor. Whether it's here, whether it's here, whether it's here, whether it's here. Okay? Because all those wires and the ammeter have 0 resistance. You do the same for the second resistor. Because it's connected in parallel, you still get 5 volts. Whether it's here, whether it's here, whether it's here, 5 volts. Okay. 0.11 plus 0.05 for the current is equal to 0.16. Currents, they add up. Using the ammeter, okay, we did that. And then you go ahead and calculate the power provided by the battery. VI for the battery, RI square for the resistors. Okay, and oh, so we finished here. What's the total power lost in the resistors and how does it relate to the power supplied by the source? We saw before, right? Did all measured currents and voltages agree with your theoretical calculations, twisting uncertainties? Yeah? Actually, they were exactly the same. Okay, if not, yeah, there was a small difference, right? There's small difference in the second or third decimal place. And here you go, result and conclusion. Write a brief 3 to 5 sentence overview of what was accomplished in and concluded in this activity. Okay. So that's the lab for this topic. Let me take a look at the next lab. Maybe we can start. This is number 6, number 7. that RC circuit. Let's see how yeah, it looks like it's a little bit long. Won't be able to do that. Let me take a look at something else. Bear with me, please. P122. Yeah, we are going to do the other one. Yeah. It is lab number, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 11, and 12 that we are not going to do. Okay? 11 and 9, 11, and 12. So let me just update here on my syllabus. I don't think I put that in my syllabus. Let's get that. 2, 3, 4, 5, 6, 7, 8, 9. Okay, is this one here that we're not going to do? A lab report. No lab report for this one. Okay. For this one, there is a lab report, and that is going to be on the 9. Eight, 9. Okay. Not applicable, right? It doesn't. Okay, so that's the one that we do not do a lab report, but we do a lab report for this one. Hopefully we have time to do RC and magnetic fields together. Okay, and maybe what we should do the lab Faraday law, all those ones that do not need a lab report, we do at the end. Let's do it this way. Okay. No lab report for simulances. That's going to be number 9. Nine 11, but there is a lab report for this one. See, that's what I did the first time I taught this course. 8, 9, 21. Okay, RC circuits. It's going to be next, like that. Next time we meet. That's going to parallel, yeah, that's going to be 7 and 8. 8 should be magnetic field. Okay. In general, we teach Faraday law before refraction and refraction, but what I want to do, I want to bunch up all those that don't have a lab report at the end. Okay. One, two, three, 4. Let's put like that. NA, NA. Okay. NA, this one. Yeah, both is going to be magnetic field. Will have a lab report. Can I do that 21? Let's see if it fits. Yeah, it doesn't fit. There you go. Last day of class. Okay. Any questions? Let me see here the chat box. We can see, yeah, you cannot see my screen? Okay, no, yeah, that's a node message, right? Yeah. You can see the screen right now, right? Let me save that as version number 4. And I will upload it as a PDF document. Okay, so that's what we have. I will stay around for the office hours. And if you want to ask any questions, feel free. And if you don't want to ask any questions, I'll see you again next week. Okay? Watch out for the notes and the videos that I'm going to post it. See you.
Thank you. Bye.
Bye-bye.